everyone. Welcome back to Interview with Scientists. Today, our guest is Dr. Kamila. And without any further interruption, I'll ask Kamila to introduce herself.
So, hello, my name is Kamila Muchowska. I'm a research scientist at the CNRS, that's the French National Scientific Center.
Yeah.
And I work at the Institute of Supramolecular Science and Engineering in Strasbourg in the lab of chemical catalysis led by Professor Joseph Moran. And what I do there is I occupy myself on a daily basis with projects that basically deal with the problem of the chemical origins of life.
Okay, that's very interesting. So, can you tell us a little bit about your education, about your PhD degree?
Okay, so my education, my academic parcours has been quite perhaps unusual because I have an engineering background. I got a master's in chemical engineering at a polytechnic in Gdańsk. This is my hometown in Poland. And that degree was in chemical technology. So basically I have an engineering background.
Yeah.
And soon after that, I moved on to the UK, to Scotland, where I did my PhD in Edinburgh in physical organic chemistry. So that was quite a change for me. So I spent over 4 years in Edinburgh, and then I changed fields again. I moved to France, to Strasbourg, where Professor Moran introduced me to the very interesting field of chemical origin of life. Which is a really multidisciplinary field, so the fact that I've changed fields so many times was quite handy at that point, because yet again we are merging different areas of science, geology, some astrosciences, and chemistry, and catalysis, and metabolism, and biochemistry. So this is a very collaborative field, and we have to bridge many different disciplines of science.
That's again very interesting. So, how was your transition from one phase to another? Was it a smooth transition, or was it a lot of a steep learning curve?
I mean, I really like challenges, so I thrive on new challenges and new things, and the bigger the problem, the better.
Yeah.
So, I don't know, I'll probably be bored doing the same thing for too long. So for me, it was a good thing to change.
Interesting. So today we are going to talk about the origin of life, the theory behind origin of life. So can you tell us about the theory? What is Charles Darwin's theory about origin of life?
Oh, so this theories that the humankind has pondered over thousands of years about where life came from mythology, and different sorts of really fantastic ideas, spontaneous creation and whatnot. So you could say this problem has a very, very philosophical, so to say, lining.
Yeah.
But it's only been a few decades, I would say maybe half a century, where scientists have started to really approach it in a scientific manner. And so like starting from Darwin's speculations about the warm little pond.
Yeah.
So that was the 19th century, but then there wasn't really a way to test these ideas, and it wasn't until the 1950s when we had the famous Miller-Urey experiment, and that is when I think everything sort of kicked off, and scientists really started to test different hypotheses. So I must underline one thing, and basically most hypotheses and most theories about the origin of life, I'm not even sure if we can call them theories in a very, very purest scientific sense, because all the hypotheses that are being proposed, they are non-falsifiable. So we cannot test them against a negative result.
Okay.
We cannot yet. if we had to go back in time and check whatever we are proposing. So over the past decades, I think the two major trends have been observed in the field, and the first one is called the genetics first. So that's where we've got those scientists are proposing that it's the genetic material that emerged and started replicating itself. You can also know that you can also recognize this hypothesis by the name of the RNA world. So these scientists are putting stress on the feature of replication and then also the catalytic function of RNA, which then later allowed this genetic material to produce metabolites and kickstart a lifelike system into existence. And something that has been put in opposition to that RNA world for a long time. And personally, I don't think it should be put in opposition. And I think the recent shift in the field is kind of following this way of thinking. But in principle, there is this other hypothesis, which we call the metabolism first one. And it proposes something slightly different. So it highlights the role of metabolism and chemical processes that sort of parallel the known biochemical pathways, and they would have built up biomolecules that would then, through dynamic processes, give rise to more complex biomolecules, which involves also genetic ones. So basically, you've got two things. So the RNA world proposes genetics to come as first, and then this gives rise to metabolism. And metabolism first proposes something exactly the opposite. So we are obtaining metabolic pathways, which later give rise to genetics. So this is a simplified breakdown of the most classical approaches to the field and to the problem.
That was really condensed. Thank you for simplifying that for us. So my next question to you is, what sort of chemistry led to the building blocks of biology?
So, like I already said, we need to remember that whatever hypotheses we form about the emergence of those lifelike processes and the building blocks, everything we are proposing is non-falsifiable, right? So the idea was of the fact that you always have to test the theories was proposed by Popper in the late 50s, I believe. So what we have to do every time if we are trying to define the sort of chemistry that led to the building blocks and whatnot, we need to provide constraints and more or less plausible approximations within those constraints. So the way we work is twofold. So first thing I need to underline is that over the past decades, many scientists have focused on building blocks. So it has been a trend. There was a trend in the field where people were sort of chasing one another, trying to propose different ways to make building blocks. But recently, I think there's again a shift in the field where we start to notice that building blocks are not enough. Because you could take all the building blocks that you have in the Sigma-Aldrich store or whichever database of KEGG database, human metabolome database, and you could put them together in a glass, stir with a spoon, and we will not obtain life. That is because life is a process. And if we want to produce building blocks, we need to pay attention to processes these building blocks can be part of. So such a process life is such a process itself. So we call these processes dissipative processes. And what's so special about them is that they are self-organized. And what this means, so for example, by analogy, sometimes when we give talks about our own research in the lab, we use this analogy of the hurricane. So a hurricane has a pattern. If you observe a hurricane from space, you see a vortex and it turns around and it has this eye inside of the storm. So, but what is a hurricane? Like, what is this vortex made of? So we've got the ingredients, we've got the building blocks, and that's water and air. But you could take water and air, put them together, stir them, and you will not obtain a hurricane. And why is that? So because to obtain this emergent pattern, you need to apply a gradient of temperature, of pressure, and this gradient has to be applied over a very specific scale. So if you apply it over a scale of 10 centimeters, you will not obtain a hurricane. It has to be over hundreds of kilometers or a couple hundred kilometers. And only then, when you have these constraints and when you have these conditions met, will you obtain a process, a pattern that is reflected as this vortex. So the same happens with life. Life is a process which dissipates energy. So for these, for example, chemical pathways that behave as like life-like processes, we need to also have some energetic stress, and only then will a lifelike process emerge. And this lifelike process will include intermediates, building blocks that will follow from one to another. But just creating these building blocks, no matter what, no matter how, it doesn't solve the problem. It has to be a process that will lead from one to another in a manner that makes sense and in a manner that creates a pattern and is self-organized into a pathway. So we need to remember about that. And I think more and more people start to approach this problem this way. We've had some results in our lab where we recreated several pathways of fragments of those early pathways, such as, for example, a carbon fixation pathway, which converts carbon dioxide to more complex biomolecules that are 2 carbons large or 3 carbons large. And we also managed to recreate parts of a reductive Krebs cycle. So this is also a pathway which is found in very early organisms, and it's considered by evolutionary biologists as quite relevant to life's origins. So these are all not individual building blocks, but we are always thinking about pathways and about patterns and self-organization. So I think this is a very important thing to remember.
Definitely, and the way you explained this was really nice. Thank you very much again.
You're welcome.
So, what was the role of system chemistry and how did cooperating homeostatic networks form and develop spontaneously?
So I think I partly answered this question in my extremely long answer to the previous one, because the processes we're talking about, the dissipative processes, we are talking about networks. And what else is system chemistry if not just the way is the approach to studying networks of molecules which interact with one another and create a function, so to create emergent properties and create dynamic patterns. And so this is, I think, the most modern approach to prebiotic chemistry has shifted from creating just building blocks as the end target to systems chemistry and looking at networks and systems and pathways that are sort of kinetically coupled to one another, which means they are dependent on one another, where you're not only looking at one chemical reaction in isolation and then some other one in isolation and then kind of hope that the products will meet and create something useful. So I think it's not the best idea anymore.
Okay. So what kind of experiments do you do in the lab? Can you give us an example?
We do experiments which are based on medium to high throughput screening. So first of all, we decide on what sort of pathway and what sort of intermediates we want to target. So what is our process? What is our pathway? So I can give you an example. For example, the simplest one, converting carbon dioxide through a pathway that follows a real biological pathway, the Wood-Youngdahl pathway, or in other words, the acetyl-CoA pathway. Yeah. So you take carbon dioxide, you combine two of them. First you reduce it to formate, then you add another carbon-containing molecule. You generate acetate, and then you add another carbon-containing moiety, and you generate a 3-carbon pyruvate. So this is our target. Yeah. And then how do we do this? So we looked at enzymes and what those enzymes do in biology, because in biology, these transformations are facilitated by enzymes. Mm-hmm. And all these enzymes contain a metal center, an active site, or a metal cofactor. Yeah. So we first focused on metals, and we thought maybe metals can replace enzymes in promoting these reactions in sort of a prebiotic setting. So we chose our constraints, as in our catalysts would be probably metals or metal salts. Yeah. So these things that would replace enzymes in promoting these reactions. We also sort of narrowed down our temperature range. Okay. So we chose roughly between room temperature and 100 degrees for that one. For many reasons. First of all, the range of temperature that life is compatible with. Yes. The life that we know. The range of temperature that is available on Earth, or perhaps was available on the early Earth. And also practical reasons. We narrowed down the reaction time. We also specified the pH that we will be working within. Mm-hmm. So that also took into account the pH that is compatible with life. Yeah. So basically we have an array of parameters, and then what we do is screen different combinations. So that leads to, depending on how many variables you have, so that leads to hundreds and thousands of reactions. So I would say for one project, for this early carbon fixation project, me and myself and another colleague, yeah. We screened about 5,000 roughly. Oh, okay. So there's also the pressure that you have to vary, the temperature, the pH, the reaction time, the catalyst, so the metal, maybe also some other additives such as salts to make it more realistic in terms of, for example, seawater conditions. So there are many parameters we triangulate, and then we look for hits. Okay. And then if we find a hit, then we optimize and try to see what to do to amplify the results that we want to achieve. So for us, it's a lot of screening. I have a slide.
Sure.
If I could, from a practical point of view, perhaps I can. I can't really share.
Allow participation. Oh, okay.
It says that you have disabled.
Oh, now it's enabled. So.
Okay. Okay. Okay, so basically what we do, like I said, we run the reactions in little tubes or little glass vessels. Usually it's small volumes because you want to maximize the throughput. Yeah. So we choose parameters to screen against, and then we identify the conditions that give you some sort of result. Yeah. It seems easy so far, but I would say that by like a ballpark figure of 90% or even more, things don't work. So those hits are not really very frequent. Mm-hmm. But then we analyze, and so basically we analyzed, at least what I worked with the most, yeah. is the gas chromatography and mass spectrometry. So that's the GCMS, which you've got here. Yeah. or we analyze by nuclear magnetic resonance spectroscopy, which we call NMR. That's here. Other members of the lab also use HPLC, LCMS, and lots of other analytical techniques, but we focus on high throughput, and we just choose the parameters within reason to find what works and what doesn't work, and what parameters influence the reactivity and the outcome.
Okay, so you choose multiple parameters, just like probabilities. Very interesting. So, if someone wants to join your lab or focus on research like you, what pathway, career trajectory they should follow?
There are lots of societies for young scientists.
Yeah.
Different astrobiology programs, astrochemistry programs. It depends on where you are based. I know there are very many different opportunities to join these societies as an undergrad, even, where you will be exposed to to information from most senior scientists, where you can take part in workshops and conferences.
Yes.
In Europe, perhaps this is a little advertising. But my more junior colleagues have established a society which is called the OOLEN, OOLEN.org, where even bachelor scientists can join, and there are meetings where you can join on Zoom for now and exchange, and there are different talks and different workshops, and you can meet more senior colleagues and ask them what they work on. You can learn a lot. I really like this idea to introduce people into the field.
Yeah.
In France, there are also many summer schools or winter schools.
Yes.
So recently I took part in a summer school for young scientists, where I did an hour-long lecture about different types of metabolic pathways and their possible role in the origin of life.
Yes.
So from what I know, there were a couple hundred participants that joined online. So that was quite a big event. So I mean, lots of these things can be found on Twitter as well.
Yes.
If somebody in the beginning of the scientific career is the early undergrad or master's student, if they are interested in these things, the easiest thing to do, I think, is go on Twitter. Click on hashtags like astrobiology, astrochemistry, prebiotic chemistry. Go on the OOLEN network, OOLEN.org.
Yes.
See what's there, and
Great. Thank you very much for your time today and for providing such insights to the origin of life, which was really insightful for me and definitely for our audience as well. And thank you for providing tips on how to follow your career path, because I know many people, many young scientists, many young students would be interested in understanding this.
Yeah, this is a very multidisciplinary field, so you don't have to be a chemist. There is work to do for astroscientists. There is work to do for geologists. We don't have many geologists in the network.
Yes.
For chemists, for biochemists, for biologists, for evolutionary biologists, for microbiologists.
So everyone.
So like there are even people who work in some I don't even know, philosophy or something. Or statistics or mathematics. So if this is your thing, I'm sure you'll find something.
Yes. Thank you very much for your time, Kamila.
You're welcome.